I'm not going to enforce it, but Mr. T will. So, yeah, that's the 15-minute A-chain you get.
And you're wasting 2 minutes of my
I will start the clock when you start speaking, which is not an excuse to mine.
So, all right. This is a celebration of CITA, and I thought I'd give a talk or speak about work that I've been doing, which actually started here. And when I started to prepare my slides, I tried to refresh my memory as to when exactly it started. It turns out 20 years ago. So as we were commenting earlier, I feel like I ought to be having a midlife crisis just about now. The work started, as I say here at CITA, when I arrived. Nick had just worked on a paper where he had taken some early observations of the cluster luminosity functions and cluster temperature functions at redshift 0 and redshift 0.3, and realized that if you compare the observations to theoretical models based on the idea that gas is falling into clusters and being shock heated, and so it's at a variable temperature, that if you took this simple standard model, if you will, that the predictions of the standard model were in conflict with the observations, and he proposed a rather flippant at the time, but turns out prescient suggestion that the gas was somehow preheated, that it had its entropy affected before it fell in, and therefore was on a different medium when it cooled into the clusters. Very soon afterwards, there were other indications that started to emerge that showed that the standard model was actually not working out well. I'm not going to go through this whole list of scaling relationships. I'll just focus on the luminosity temperature relationship because it's quite well known. The blue curves there show the prediction of the standard model, and you can see that on the cluster scale, if luminosity scales as temperature squared, whereas the observations were showing a slope that was more compatible with luminosity going as temperature to the 2.7 or even 3. There's also the offset in the normalization that shows up in the mass temperature relationships, etc. And so there was this larger problem that was emerging, that clusters which, when I was going through graduate school, were dull, boring, and well understood, were suddenly not well understood. And as it turns out, one of the reasons for speaking about this 20 years hence is that the field still is perplexing, puzzling, and in fact, Christoph, who's a young fellow, tells me that it's very interesting, and people should be getting into cluster physics. Anyways, we started working on preheating, the picture that Nick had sort of speculated about, and showed that if you did include preheating into models of cluster formation, that you actually started to get the scaling relationships correct. The mass temperature relationship comes out correct. I draw your attention to the red curves in these relationships. The luminosity temperature starts to come out right. Note that even on group scales, we actually get this bump that turned around, whereas the standard model actually deviated away from the observation. Now, groups are a problem even today, and a lot of my present-day work is trying to work out a scheme where we can start to probe the group population, because I think that the proof of what we're arguing is happening on cluster scales actually should be there on group scales, if we can only get the right observations to demonstrate this. Now, I haven't told you what I mean by preheating. The early paper that Nick wrote about preheating didn't quite flesh it out. We, in late 90s, went through the calculations a little bit more, and the generic picture that we arrived at was that, well, you need to have well, we knew that there were starbursts starting to be seen, and starbursts were believed to be associated with epochs of galaxy formation. The epoch of quasars, the peak in the quasars, number density as you go backwards, appeared to occur at about the same time. There were observations of high velocity winds starting to come out at the time. Our picture was one where you had this powerful feedback driven at the time. It didn't really matter initially whether it was purely AGN or AGN plus starburst. The AGN component was important because we just couldn't get enough energy out of starbursts by themselves, particularly on group scales. On galactic scales, starbursts worked fine, but on group scales, AGN component was important. The basic idea was that powered by AGNs, you had outflows that then emerged from the galaxy, shocking and heating up the gas out into the wider environment, the protocluster environment, if you will. Now, that picture, when you work it out, you'd expect there to be variations in the level of entropy that the gas ends up on, and that variation, in the very simplest way to think about it, depends on the background density. So if you do these explosions early on, if the galaxy formation in a particular region occurs fairly early on at high redshift, then the background density is higher, and since the quantity, I'll show you in a minute, or I guess it's here, the quantity that I'm describing as entropy is not really the thermodynamic entropy, it's the conventionally used proxy for entropy. It's kT divided by density to the 2/3. This quantity with a higher density in the denominator, the entropy level is lower. If this process occurs at a later time, the entropy that's generated is higher, so you'd expect there to be variations with respect to entropy generation from region to region. And
why are you assuming that the energy is also not different?
No, it's not. I'm just pointing. The energy will also be different, and it'll depend on how much accretion is occurring onto the black hole. So yeah, no, there are many other effects that come out. My main point is that you expect there to be variations in both the energy and in the timing. The timing issue gives you the density variation. So entropy will vary. You know, the idea that there'll be a uniform heating occurring in all protocluster regions is what I'm just trying to steer you away from. At that time, the idea of AGN feedback was relatively new, and simulating the ripple effect of AGN feedback from galactic scales up the hierarchical chain was virtually impossible. It still isn't easy, but starting to become doable, and I'll just mention this in the middle in a couple of slides down. But that was a picture. I should mention that I'm actually cheating a little bit. This image that Tom Huns lent me was not showing feedback occurring on due to AGN feedback, but it's rather ionization picture. But it looks pretty enough and serves its purpose in terms of conveying the right idea that we had in mind. Since then, AGN feedback has become a de facto feature of galaxy formation. More commonly, it is invoked in order to shut down star formation in elliptical galaxies and stop them from turning out too blue and much too luminous at the present time. Now, as I mentioned, simulations had a while to go, and in fact, the first set of simulations that are starting to do or starting to look at the problem the way we had conceptualized it about 10, 15 years ago are just starting to happen now. I've listed here a group of people who have been doing simulations that are working along these lines. There's the Ian McCarthy, Job Shea, Volker Springel and company, Deborah Seljaki, Christopher Cromer from right here at CITA, also Volker Springel and company have been doing the same thing, and Romain Tessier and company in France and Zurich have been doing that. And in fact, I was in Zurich a few weeks ago, and we were looking at the simulations that he had done much more carefully and analyzing them. And the interesting feature out of Raman simulations, at least, was that when you had these feedbacks going, you indeed start to see the shocks and wind being driven out, and you will see heating occurring on fairly large scales, certainly on scales that transcend individual galaxies and spread out into protocluster regions. Now, that's the preheating picture, and the plots that I had shown you earlier about the scaling relationship sort of assumed a mean relationship with respect just a single core entropy value. But there's a bigger puzzle in the picture, and that's the scatter. So here we have, again, the temperature luminosity, and if you look, you'll see that at a given temperature, there's a factor 10 spread in luminosity. You can get similar types of relationships when you look at the correlations between the Compton Y parameter and the X-ray temperature, etc. Now, you cannot explain this large scatter by a uniform preheating. And the question that started out was, where did this preheating, where did this scatter emerge from? Our picture was, as I indicated, was from the variations in the protocluster phase with respect to preheating. But there were other pictures around, and the argument that was often given to us as we tried to push our particular picture was that the non-cool core clusters, so systems with higher entropy, were in fact transformed cool core clusters. So you're basically taking these systems, somehow making them into those possibly as a transient, and then they settle back down into the cool core state. Now, we do know that there are mergers happening in hierarchical models, but as it turns out, mergers are not capable of turning cool core systems into non-cool core systems. For one, the dense cores are extremely resilient to being heated up and disrupted. And you need massive mergers, 3 to 1 at the very least. Most likely, generically 1 to 1 are the ones that can do it. And even then, the 1 to 1 mergers will only disrupt the cool cores for about a gigayear. Now, when you look at the distribution of cool cores and non-cool core clusters, it turns out that there is half and half. So you need to do this in about at least 30% and as many as 50% of the systems. And that's a problem. I'll skip this. The second hypothesis was that you had a cool core system, you had a massive AGN outburst occurring in the system, and you transform the massive the cool core into a non-cool core system. You can go ahead and work out the energetic requirements that you need if you have a cool core system and you blow a bomb off at the bottom of this thing. It turns out that you need of order 10 to the 63 ergs to change a cool core system with central entropies of about 5 to 10 into something greater than 100. And this exceeds the energy output of the two most powerful AGN outbursts that we know of, Hydra A and the MSO735. And of course, you need to arrange for this in 40% of the clusters. Our picture was one where preheating would give you a variation in the central entropies. And so you have a variation in the central entropies, and that these variations would map onto the scatter into the LT relationship. When we first started to push this picture, this was the results from the Chandra archive. So you can see here the entropy profiles in clusters, they all dove straight down, there was no core. And then a few years later, and then very recently. And you can see the range in these core entropy is now spanning from a few to as high as 600. So you really do have a fairly large distribution of core entropies in clusters of galaxies. And the lines there that I've shown sort of divide out classical cool core systems, and non-cool core systems. Hank talked about this a little bit, so I won't belabor this point. If you look at the cool core systems, the basic idea there has been we see that the gas is not cooling out as rapidly as it should be if you just did a radiative cooling calculation. And the common argument is that AGN heating is balancing cooling. We see effects of AGN heating occurring. For the CCCB sample that Hank talked about yesterday, we have looked at the BCGs, we've looked at the color profiles in the BCGs, and deep in the centers of these BCGs, systems that happen to be in cool core clusters always have blue cores. There is star formation going on in these systems. Some of them have star formations that have been estimated from a variety of different methods, and they have star formations of 10 to 100 solar masses. They all seem to have molecular gas. In contrast, the systems, BCGs in non-cool core clusters have a red core, and they have no indication of star formation. And this basically shows what the stellar populations are. In the red core systems, you have stellar populations that are generically 2 gigayears or older. In the blue core systems or in the cool core clusters, you have the BCGs where you do have a small fraction of the stellar mass that is very young. It is younger than 200 million years, and there is no indication that the star formation actually stopped. What we're learning here is that the AGN is not stopping star formation, it's tempering it. It's slowing it down, but it's not stopping it. And if there is a duty cycle occurring, that duty cycle must be shorter than 200 million years. I'll just mention one since my time is about to run out. The fact that when you map out the distribution of cluster core entropies, you find that that distribution has a bimodal feature. Cavagnolo found this. Al Sanderson at Birmingham has now found this. So there's a growing indication that this is a robust result. And we've been trying to understand more recently how you can establish this kind of a bimodal distribution. Of course, one not very palatable way of thinking about it is that it was set in ab initio, but then that requires that this peak was much further over, because even though cooling timescales are long, it does evolve down. And so you need to set a bimodal distribution to begin with and heat it up to a higher temperatures and then allow it to evolve. There are other ways of doing this. You can have secondary mechanisms, and one secondary mechanism that we've been looking at is stirring by galaxies, stirring basically dynamical friction. Galaxies are suffering dynamical friction, that energy is going somewhere, fraction of that energy is going into the gas, and that gas is heated up. Now that picture has been looked at by a whole host of people in cool core clusters. Last slide, second last slide. In cool core clusters, the dense core is such that this secondary heating is completely irrelevant. So this little trickle of heat makes no difference. The central regions are so dense, they're losing energy much more rapidly. And so you can see here the difference between pure cooling and pure cooling with stirring makes absolutely no difference. But if you start something up with a higher entropy core to begin with, then the cooling times are long. The radiative losses are much less, and stirring is capable of offsetting this particular effect. And so you actually have a population that will more or less remain stable. And I'll stop that. Just show pictures of a toy model where we evolve a population of galaxies, and you can see that this peak more or less stays intact, and that's what it ends up looking. I'm out of time?
Oh, yes.
Stop there.
First question. Next up is Nick Battaglia talking about simulations of clusters of AGN feedback.
Thank you, John. So I'm going to be presenting some work that we just put out on the archive. This is work done with my supervisor, Big Bond, Christoph, John, and Deborah Sajaki, who's at Cambridge. So I'll be talking about simulations with large-scale structure with AGN feedback, and a lot of the background Arif has already gone through, so I'm going to go pretty quick. So our motivation here is to use galaxy clusters as a cosmological tool. That's not a joke. That's really what we're trying to do. And we're doing this. The main focus of my talk is going to be the CITA power spectrum. So actually, just recently, a couple of weeks ago, Gil Holder described the theoretical modeling of the SZ power spectrum as a theoretical train wreck. And I don't see it that way. I actually see it as more of an opportunity to and what's pushing our theoretical models right now are the results from ACT and SPT and soon Planck. They're coming out with results, and well, there's already been ACT and SPT results on the SZ power spectrum. You can also use clusters with X-rays and the optical, as I mentioned. But we're really focusing on, like I said, the SZ power spectrum. This is one halo analytic expression for the SZ power spectrum. You can also, so you can study it analytically, you can study it through SkyMap. So this has been done in the past. This is not an exhaustive list, but it is a list of some of the work which should be here. And we are doing both. We're looking at both analytically, solving, coming up with a nice pressure profile. So this is where most of the gastrophysics, as they call it, comes in. This is the Fourier transform of the pressure profile, the square. And this is where a lot of the message comes in. So it's really important to get the gastrophysics correct. And this is just, that's an SD SkyMap from So, like I said, it's important to model your ICM correctly. And so to do this, you've got to match the X-rays, you've got to match the scaling relations, you need to match the profiles, which are harder to do than the scaling relations. You need to have the appropriate fraction of gas within your clusters. You also need to do this for, you need to match the SZ scaling relations, power spectra, and future SZ profiles, as well as you need to have the appropriate number of stars. So there's many ways to tackle this. Like I said, you can do it analytically. There's lots of problems with doing it analytically. There's asphericity. You have to assume hydrostatic equilibrium at the moment. How do you account for non-thermal effects? With simulations, you have the problem of, well, your simulations, you have to add in a lot of subgrid physics. So subgrid physics like star formation, and this inevitably leads to the problem of overcooling within your simulation, which is a problem we had to tackle. So this is just an example of overcooling. You can see from Christoph simulations with cooling. You get your temperature profiles, and they actually plunge down in the center, and you get these density spikes in the center. And you also overproduce stars, and this affects your thermal properties. Like I said, the SZ power spectrum is dependent upon your pressure profile. So you need to get the thermal properties of your clusters right. So our model, I'm just going to give you the punchline right here. It does really well in our model for the ICM. In our simulations, we get appropriate scaling relations, we match observational profiles, we have the appropriate gas fraction within our clusters. We do well to match the current power spectra results. We don't overproduce stars in our simulations. Because we don't underproduce stars. And so it does pretty well. And how did we do this? Well, we added we introduced a form of put in quotations AGN feedback. It's loosely modeled on AGN feedback, but it's a form of feedback within the clusters, which solves this overcooling problem, which I'll show you, and does really well in matching these observations. So just a quick sidebar. There's been lots of work on AGN feedback, as I said. So there's people that use an empirical relation, so a Bohr relation to model their feedback within the simulation. So this is Rob, who we heard yesterday, Deborah, some others, and they've run these on a lot smaller scales, so not cluster scales, but more galaxy scales and quasar scales and group scales. And then there's another group of simulations led by Volker, Deborah, Yokshe, and they use they estimate the bonding coil accretion onto their clusters. I like to highlight the word estimate because last time I gave this talk, I said they use bonding coil accretion, and Rashid told me no, they do not do. They do not resolve bonding coil accretion. They only estimate it, and they have this factor here, alpha, which is about 100. So quickly, our model is a subgrid model, very subgrid. We try and model things that are 10 to 9 orders of magnitude smaller than the resolution of our simulation. So, you know, the accretion onto the black hole scale is AU and less, and we are simulating stuff that is kiloparsecs, several kiloparsecs is our smoothing length. So our model is simply, we can go into more detail offline, but we simply say that the accretion rate onto the black hole is going to be very similar to the star formation rate. And from that, you get an energy injection that is just some efficiency factor here, the star formation rate, c squared times some duty cycle. And we do this spherically within our clusters within a given radius R AGN. So the parameters, the three basic parameters of our model is this duty cycle, which is about 10 to the 8 years. We have this efficiency parameter, and then the radius, which we choose to inject over. So there's a lot within this efficiency parameter, and there's a lot actually to it. It's not, you can't consider it as an integrated efficiency number. So first, let me say, so this efficiency has in it the scale from the star formation rate to down to the black hole accretion rate, which is about 10 to the 3 in difference. There's also the efficiency of the matter accreted onto the black hole, how much of that is radiated, and then you're coupling your radiation to the actual ICM. There's another efficiency there. So that's all included in our parameter epsilon r here. And so our parameter epsilon r is about 10 to the minus 4, 2 times 10 to the minus 4 is what we use in our simulations. This is not, like I said, you can't consider that to be the efficiency. If we look at it another way, if we calculate the total energy we inject over a given, or run the simulation, and we calculate the total number of stars produced within a given radius, that gives you more of an idea, gives you more effective efficiency within our simulations. And so we tune these parameters here to try and match previous AGN models that we know to do fairly well. So we chose Deborah's models to calibrate our model to. So, quick note, so our simulations, we use Gadget. We have simulation of a single cluster. This is what we use to calibrate. So it's a D616. That's how we calibrate our feedback. We also run several cosmological box simulations. This is where we do most of our actual cosmological work. So we have several models. I'm just going to be focusing on the AGN feedback model because for lack of time. But I'd like to plug SciNet, which has many computers, and we've run several simulations. So and they saved me a lot of time. So I'd just like to thank that, and also I've done some on this is Sunnydale, not. So. We also have the ability on SciNet if we want to go even bigger. So we've run 256 cube simulations. We have 512 cube simulations, and if we really wanted to, we can push the limit, but we haven't done that yet. But it is in our plans to go even bigger. So let's get to some results. So this is our model calibration and comparison. So what we looked at is we looked at the fraction of stars within a given radius. So this is again a radial profile, and the orange is Deborah's model, Deborah's Jagged's model. The red is our model, and what we did was we tried to tune our parameters to recreate their model. So the solid is fraction of stars, the dot is fraction of gas,
And I've also included on here some data. So this is optical data. So this is fraction of stars from Gonzalez et al. For a similar size cluster as G76, and we do pretty well to fall within there. And so our models are red without feedback is blue. And also there's a point on here of F-gas that NIAC provided us with. And our model actually goes to both, so we were pretty happy. This was not, so initially these points were in here, this was added on later on. We were initially just trying to recreate, in the worst case scenario where we had really high resolution, what Devon's model did, which requires such high resolution. So, comparing to more observations, what we have here is I've plotted, we just need to focus on the band, which is stacked X-ray profiles from Arnaud et al. This is the re-access sample, which was just published in 2009, and the thick red line, which is our pressure profile. So what I've done here is this is the pressure profile scaled by the radius cube. So what you're actually looking at is the energy d ln r. And this is a function of radius, and so you can actually see where your contribution will your contribution to the SZ and OL will peak. So I broke here. This is a bonus. We didn't actually, like I said, we tuned our model to our parameters to kind of match Deborah's results, and it turns out our model does actually extremely well to recover or mimic what's being done or what's being found in the X-ray observations. So on to the actual the meat of our so this is the SZ power spectrum. This is a Bondian plot. There's a lot of information on here. But what you really need to focus on is the red points. These are from our simulations and our three different models. The red circles are the AGN feedback. And what you can see is there is not that much difference at low L. But when you get to higher L, you can start to distinguish between different models for if there's feedback or not. And this is actually, as we show in blue points, is really dependent upon what's happening at higher redshifts. So redshifts beyond 1 is where we can really start to constrain our models. You should also take away that we do fairly well to match previous results from DIG, from Springwhite and Turnquoise. And these were done a lot earlier. And there's also the lines here are from analytic and semi-analytic calculations of the SZ power spectrum, which we go into. There's a lot of comparisons in the paper, but for time's sake, I'll leave it there. So these are calculated just quickly from our simulations, which we rotate, stack, and translate in a stat map along within redshift space. And finally, to the cosmological constraints. So we take our templates, we put them into Cosmo MC, we run them, and we get what's called your amplitude of your SZ power spectra. And from previous results, this was actually coming out fairly low. So if you get an AZ at around 1, it means you're matching the current fiducial cosmology, or WMAP7 cosmology. And previous results we're getting, or previous templates used to get the AZ, the amplitude of your power spectrum. We're getting much lower results. We actually find so that we show our AZ within the power spectrum space here with the dark gray band, and our result is the two red lines here. One is with including kinetic SZ spectra and without, and we find that both are consistent with the current results from the session. So my time's up. I'll leave you with our AGN feedback model does really well to recreate X-ray observations, SZ observations, optical observations, and we are currently consistent with WMAP7 results for sigma 8, and there is much more to come. There's a lot more I was supposed to say, which they told me to say, but I probably forgot. But thank you.
So, what exactly is your sigma and what error is on that?
So I'm not allowed to. So we don't like to refer to what the sigma 8 is, but I can tell you what it is. John will get mad at me later, but our sigma 8 right now is 0.75 with an error bar above 0.05. But the more important number, which is less important, is the ASZ number, which we get, which is about 0.75 plus or minus 0.35. If we include KSF, that becomes a little worse. It's marginally consistent, so it's about 0.65 plus or minus 0.35. But those numbers are all in favor.
No, there's also still uncertainty in KSF.
There's lots of uncertainty in what we do for the case.
All right. Thanks again, Nick. She was not ready. She was almost ready. What's that 11 now? Yeah, I don't need that. That 11 is really Monday. Try and sneak in. Wedding cakes and brewers.
Okay. So we have this thing. It's projecting over there, but it's not projecting on the screen over here. So every time I come back to CITA, Margaret always asks me, some point or the other, whether I'm happy to be back in Toronto. And the answer is always yes. And so happy to be back again, and Dick and Bob again. So as I looked into the schedule for this session, the first two talks are completely theoretical, or simulations, and the next two talks are observational. And I'm bang in the middle, and I'm quite happy about it because I like to be in the middle. Because I need to talk about simulations, observations, and I'll stay halfway. So I'm going to talk about wedding cakes and rulers. And to go ahead, let's just see why do you want that. So all the cluster surveys that we know of that's happening right now, like ACT or South Telescope, Planck, CITA coming up maybe in a couple of years, all wants to do clusters, cosmology with the main goal is to do number counts. And basically, it wants to look at numbers in redshift bins, and that is connected to the mass function and the volume. And the previous two talks basically concentrated on this, which is the physics that connects the masses to the observables. And so cosmology can be done once we know this relation very well. So if you don't know this relation well, then you cannot do it. That's the main. And so people have thought of ways to go ahead. And first of all, the first thing to do is that you can go bottom up and try to find out what's the physics that's been going into all these things and see if we can get this relation. And if you are quite confident about this, that you can really match this relation and you can use this relation to go from the observer, which is maybe as a flux, the velocity, whatever, to the underlying mass of the cluster. However, if we don't know this relation very well, for example, we don't know the amplitude, the slope, the scatter, if we don't know the evolution, Then there's a question, and basically what will happen is that your customer information will be diluted and will probably not get the right response. And that has always been the problem for customer response. So whether people trust it, whether people know what's going on, and once you go, find ways to go beyond this. So people have thought about this, and before people used to really bother about this is almost 10 years back. Baylor and I told over to this other paper, and they showed that if you have lots of clusters, and these are like output plots of sigma and omega matter, sigma and omega matter, and W0, and these plots are labeled by the number of clusters in that service. This is a really small number of clusters, larger, larger, larger. And these were like the numbers that people call the SPT or ACT would get, SPT would get. And the thing was that then you get very small interest rates, very technical. This, of course, assumed that you know your cluster scaling relations completely well, so they had a fixed mass limit, and there was no uncertainty in cluster physics, so it's unrealistic, but it was good at the first attempt 10 years back. Now, as soon as you put in your uncertainty in cluster physics into it, even with this kind of numbers, these error bars become bigger, so the smallest one will become like this, the blue one, and so you have to think of something to sort of overcome this. Now, there have been two main ways to go about it. One is to have a targeted mass calibration from a large sample, and so people showed that if you can have unbiased, this is actually a crucial word, if you can have unbiased mass estimates, maybe density or something, of a small number of clusters. So people were thinking at the time that the service would get tens of thousands of clusters, but you can do like 100 clusters, good mass estimates, but then you can basically go back and put those scaling relations and get your response. Of course, it needs follow-up this costly. The other thing that sort of made the way people were doing cluster surveys was the idea of self-calibration. In this case, we took the cluster physics and cluster parameters completely unknown and sort of calibrated them within the survey itself by using complementary information from counts in cells or power spectrum or whatever. And so these two were the two main ways where people tried to, other than really going and putting in the physics and knowing about it, try to bypass the cluster physics part of the cluster cosmology. Now, one crucial thing about both these is that both of these in service have large keys. You have some calibration, we need many, many thousands of clusters. So, what is the forecast that we were doing, and what's the data? So, pre-2009, SPT ACT service forecasted something like 4 to 7 clusters per degree, depending on what kind of sigma you put in the mass scale. And flag was like 1,000 or 3,000 clusters. Post 2009, when the service really came up and started doing clusters, what we have is around, so the SPT recent paper by Mandel, they had like 22 clusters in 170 degrees. It's like 1 2 clusters per degree. ACT numbers are very similar. So even when the sensitivities improve, and we also get like high energy clusters, get bigger, but it will never be like this. So it will be like 1 to 1.5 clusters. So instead of having like 10, 15,000 clusters, maybe at the most we have 1,000, maybe 2,000 clusters. So when we have this, all that we try to do is the self-calibration with this many clusters. That's not going to happen. We are still going to end up with very large error bars. So what do we do? So mainly this talk about trying to find, is there anything else that we can do with these clusters? Okay. So what's the implication? The implication is, of course, that the cosmological constraints are washed out. And the question that I ask is, so building cosmology with cluster number count becomes secondary science for this kind of service. If you're not getting the clusters, then how are you going to do cosmology with cluster number counts? And so we need to do something more with the service to come up new ideas. So the first is this idea of one that we will talk about. This is change in the way we do this service. And going from the way the surveys are made, like large 1,000 degree survey or 2,000 degree survey, into a weighting cage kind of survey. And so what we have done over here is that let's take an example of ACT. Let's say it's 2000 degrees in this kind of time, the total period of the survey. What we do is that we take the total period, so we cannot increase the observational time, but we divide the survey into two patches. One which is 1800 degrees and one which is 200 degrees. Of course, it can be any ratio can be there. And the time in each patch is divided so that there's a fraction of time between the small patch and the other fraction is the large patch. So basically what we're doing is that this is sort of a deeper survey in the sense that the redshift is still the same, redshift cover is still the same, but it's deeper in flux into a mass. Now, what does it have? And immediately when we do that, we find something very strange. So if you look at this case, there's one such case with some flux in it. This is like a flux rate of around 10 millijanskeys, but this is even much less than what people are getting now, but what can be for other fluxes also. So if we have, look at this plot. So what is the main reason why smaller surveys don't have enough cosmological information in putting construction basis because of this deviance to cosmological variables and superparameters. And so here is a plot where I have plotted sigma 8 over here, and gamma is some unknown evolution of cluster scaling equations. Now if you look at this cigars over here, this very long red cigar, this is what you get if you have this 1800 square degree survey, and instead of like 10,000 clusters, Similarly, if you have the 200 degree survey, you will get something like this. It will be even larger. Now, if you had a 2000 degree survey, the original survey, you will have a similar to this one, this 1800 degree. It's like this. But look at this. What happens is that because it's like CITA-like ellipse, as soon as you rotate it a bit, what happens is that as soon as you add the 200 degrees to 1800 degrees, you do not increase your cluster numbers. So it's not that a total cluster field has increased, but just you have one patch with a deeper flux limit, another patch with the original flux limit. You end up with a constraint which is this red boundary. Now, you could have said that, well, instead of adding these two, you could have doing a mass follow-up, like a 100 cluster follow-up, targeted follow-up. So if you have done that, this two has been the ellipsis. But even then, you see that adding these two things breaks the region and makes paradox. The same thing over here. So what has happened is that by a simple change in your survey strategy, what has happened is that we have sort of broken with much smaller number of clusters, broken the degeneracies. Really. So here's a plot which shows what's happening. There is the error bar on W, let's say, a constant W, which you think we'll get from these surveys. And if you look at this plot over here, these are different unity fluxes in the cluster surveys. This plot at the bottom, where it's almost flat, is when we think the cluster surveys have absolutely no cluster scaling relations. And so we do very well. 870 is sort of the flux limit. This corresponds to a flux limit which ACT is operating right now. It's like 30 milliamps. And as you can see, if we do this, the kind of error bar we get on W is 170. That's really ridiculous. It makes no sense to do. However, as soon as you start adding, it sort of goes down. And so whichever be the sensitivity of the survey, adding it actually, so this is like 1800 over here, 200 over here, but anywhere in the middle, the fraction, adding it, but all of them comes down, and it comes to very close to what would have happened if there was a known cluster scaling relation. So just by breaking those degeneracies by going deep and wide, we're doing pretty good. And this is when there's follow-up, and you can see these are like Markov chain results that follows the single calculation. So you see the same thing, up and down, and then down. Okay. So we can also change your area and see which is the best area time combination. And so the nice thing over here is this. So first of all, look at these two relations. As you can see, single survey 2000 degrees, look at the constraints and then compare it to the survey, which is again 2000 degrees, but 200 plus 1800. There's a huge improvement in all the parameters. If gamma, when there was unknown scale evolution, having this actually breaks it. So there is a factor of 4 improvement. And the really nice thing is that if we had a follow-up, we know that it helps in getting strong constraint, but doing this is actually better than the follow-up. So a change of strategy basically simply makes wonders in this case. This is one of the processes. Now, in the next 2 or 3 minutes, how many minutes left? Okay. Now, of course, if we say that we don't want to change this strategy, we're going to basically do 2000 degrees anyway. And then what do we do? So we're going to come up with this 1000 clusters. So we cannot do DNDZ in much with 1000 clusters. So the second idea is, well, if you cannot do DNDZ, use them to get H and Z. And this is what supernova is anyway doing. So we're going to do something very much like supernova. To do that, we need extra observations. And well, there are extra observations because the university is coming up in a couple of years. So we have same patch of the sky, which is the same volume of the sky, which has both SZ and X-ray. So what you can do is I can image the cluster the common in SZ and X-ray, and use this cluster as an ensemble of rulers to get G as a function of Z. Now this is already been done with targeted clusters. This is from Bonavente et al. They are like 38 clusters done with Chandra and Ovro. And as you can see, it's a large universe over here, but you can have an H of Z or G of Z function. With surveys, we can do similar things. So there's a cartoon over here. Let's say we combine an SZ survey with an X-ray survey. So this large one is the clusters detected in SZ, the cluster in X-ray. There will be a common number of clusters which will be detected in both SZ and X-ray. This will be the function of redshift because. And then from here we'll have another subsample for which there will be cluster will be big enough because of this stuff that we can get the temperature of it. And then there will be another subsample which cluster will be even large enough that we can have some kind of profile fitting against it. So we end up with a small subsample out of this whole sample from which we can actually construct DA like this. So this is constructed out of 450 clusters that can come up with accuracy and velocity. And if we do that, as you can see, if we had only this accuracy and DZ, it was completely useless. This is a large error bar. But we add the DA from this, you actually break the things. It becomes small. I mean, this is something that you can do. Similarly, if you can think of overlap between Eurocita and Planck, whatever clusters Planck will get, Eurocita will get. And you can see that depending on how many clusters are there in the final sub-sample, you can have different kind of states. And it's better. And all the time, what we are doing is basically we are actually having an improvement of factor 2 or 3 in the figure of merit in the total outcomes, just by getting this DA form. One last slide over here is that how does this DA compare with DL from supernovae? Because supernovae is already doing DL. So over here, this is your ACT SPT's really large degeneracy, and this would happen, this blue one would happen if we added a union data supernovae. Union data is around 400%. Whereas this green is when you have this DA from this overlap of ACT SPT and velocity. So as you can see, and whether you get this DA from clusters are very much like DL from supernovae. So it's like before pre-jet, and this is the kind of things that you can do within clusters itself. As you can see, the error bars are very similar between supernovae and. So there are 2 points to take home. The first is a wedding cake or a multi-tag. I've done 2 tags, you can do multi-tag. Survey for the same total duration of the survey with very similar cluster reads and much less cluster reads than purpose forecasted before can give strong performance constraints. Just because just when it's change in service strategy that frequently reverses. That's one thing. And if you're not going to do that, then the few number of clusters you're getting, if you look up with the Eurocita, you'll get the same clusters in Eurocita. And basically what you do is that you can get your DAZ from a joint analysis of Eurocita and this is just like DAZ from Subba. So these are 2 things that you can do with clusters without going into the itself.